How does the Boltzmann constant define entropy? Imagine trying to understand how tiny particles like atoms and molecules influence the big picture of heat and energy. That's where the Boltzmann constant comes into play. It acts as a bridge connecting the microscopic world to what we see in everyday life. Entropy is all about disorder or randomness in a system. When particles are more spread out or arranged in many different ways, the system has higher entropy. Think of a room that starts tidy but gets messy over time. That's an increase in entropy. The Boltzmann constant is a very small number, about 1.38 times 10 to the power of negative 23 joules per Kelvin. It's a fundamental number in physics that helps us measure how microscopic arrangements relate to larger, observable properties like temperature and entropy. Now, here's the key idea. Every system has a certain number of microstates, which are the different ways particles can be arranged while still maintaining the same overall energy and volume. The more microstates there are, the more ways particles can be arranged, and the higher the entropy. Ludwig Boltzmann created an important equation that shows this relationship. It states that the entropy of a system equals the Boltzmann constant times the natural logarithm of the number of microstates. In simple terms, the equation is entropy equals the Boltzmann constant multiplied by the logarithm of the number of microstates. This equation tells us that as the number of microstates increases, the entropy increases too. The Boltzmann constant scales this count into a measurable quantity. Without it, we wouldn't be able to connect microscopic particle arrangements to the macroscopic property of entropy in units we can understand, like joules per Kelvin. When a gas expands to fill a larger space, the molecules have more possible places to be. The number of microstates increases, and so does the entropy. The Boltzmann constant helps us quantify this increase, explaining why the process happens naturally and spontaneously. This connection makes entropy more than just an abstract idea. It becomes a measurable property grounded in the behavior of particles. That's why the Boltzmann constant is so important. It helps us understand how microscopic chaos leads to macroscopic disorder, and how this disorder drives many natural processes. In short, the Boltzmann constant defines entropy by translating the count of microscopic arrangements into a clear, physical measure of disorder. It allows us to see how the tiny world of atoms influences the big picture of energy and spontaneity in the universe.